Okay, so what we're going to be doing here is we're going to be looking at some equations, some certain identities, and the derivations I'm not really going to hold you accountable to, but it's something that you are going to need to know the formulas. So if I'm not going to hold you accountable to certain derivations, why even talk about it? Lots of times when you're looking at math equations, it seems like it's a mystery, where it just abracadabra, it appears. And sometimes when you have that kind of mystery surrounding the equations, it's a little more complicated to understand what's going on. So if you can remove that mystery from it, and you can see what's really being played on the inside, you get a little more comfortable with what's going on with the equations. So what we're going to be doing is we're looking at something called angle sum. So we're going to look at how it's going to, if we add up some sums of your angles, what's going to transpire. In particular, what I want to do is look at what's going to happen when I take cosine and I have two angles called A and B. What's going to happen? And what would happen if I looked at maybe the sine of A and B? Well, to start off with, what I want to do, look at a triangle. Maybe a triangle like this, where I'll have some kind of measurement. And I'm going to take the triangle and I'm going to tilt it. I'm going to rotate it. So I'll have a measurement going up this way, an angle of A, an angle of B. And if I do that, this point then is going to become cosine B, because again, we're going to stay on the unit circle, and we're going to have sine of B. Over here, we're going to get cosine A rotate it down. Okay, so if I take it and I rotate it down, it might look a little bit like this. And since I'm on the unit circle, when I take this and rotate it down, this point now is going to be on the x-axis. So that's going to be 0.10. If I take it and rotate it down, the angle that I'm going to be making, as I make from here to here, that is going to correspond to the difference of A minus B. So I go so far up A, and then I'm going to drop it down by B. So I got to take B off, and that gives me the angle from here to here. The key in the problem is making this simple observation. It's the exact same triangle that I'm making. I'm just reorienting it. I'm taking it and I'm rotating it. So what's the distance between here and here? This distance from here is the exact same distance that you would have right there. And that right there, that's the key in the problem. If I want to find the distance between 2 points from this point to that point, well, I can use the distance formula. So I'd have my point, cosine of A minus cosine of B, sine of A, or excuse me, added, sine of A, sine of B, all squared. Well, again, it's the exact same distance from here to here, so I can also apply that distance formula. Now, if I go up to this point is going to correspond to cosine A minus B in sine A minus B. So take the distance formula. We'll have cosine A minus B, subtracted off 1, quantity squared, added to sine A minus B, subtracted off 0, because y is 0, all squared. And there it is. Okay, so the next thing is, I just want to clean this thing up. This is looking pretty nasty. Square both sides. By squaring both sides, we're going to get rid of the radical. And so we'll have cosine of A minus cosine of B, all squared, sine of A minus sine of B all squared. And over here, same thing. And we do have sine of A minus B minus 0. So let's just go ahead and say sine of A minus B. Okay, now we're taking cosine of A minus cosine of B. We're going to square it. And whenever you see a binomial, we can expand out by applying the binomial theorem. Cosine squared of A. So take the first term, square it. This term times this term. Times it by 2. So 2 cosine of A, cosine B, and don't forget the last term, square the last term. So that's going to be cosine squared B. It is the exact same thing as looking at A plus B quantity squared. You have A squared plus 2AB plus B squared. It's just in the first one, A corresponds to cosine of A, capital A, and the little b corresponds to minus cosine capital B. Apply the identity right here, get that expression. Okay, now for the next part over here, you'll get the same idea. You'll have sine of A minus sine of A, sine of B, and then sine squared B. I do want to clean this up. And whenever I start seeing things which are being squared, well, that makes my spidey sense really tingle. Because I know a special identity known as Pythagorean theorem. Sine squared theta, cosine squared theta equals 1. Look what I have right here. Look what I have right here. If I combine those together, what do I get? I get 1. What about this part? And what about that part? I combine that together, what do I get? I get another 1. And that leaves us with this piece and that piece. Okay, so take everything, drop it in. Now we have the other side to work with. Apply the binomial theorem again. Well, look at this. Look at this, look at this. I see a cosine squared. I see a sine squared. And I see that they have the exact same angles. And if they have the exact same angles, this piece collapses down to nothing more than 1 due to the Pythagorean theorem. Sine squared theta plus cosine squared theta equals 1. That's going to leave us with minus 2 cosine A minus B plus 1. But 1 plus 1, that's 2. Well, look at this. Why not subtract the 2's off? And then why not divide both sides by -2? And if we do so, we come up with our first identity. Cosine of A minus B corresponds to cosine of A times cosine of B, flip the sign, positive sine of A, sine of B. All right, now this is what we want to know the formula. How we got there, all it's doing is it's just revealing that these formulas, they're not mysterious. There's actually some reasons why they come about. Okay, well, what about cosine of A plus B? How can I use what I already know, build upon my knowledge to get a new identity? Well, look what we can do here. You could take this and you could recalibrate it as such. What's a minus times a minus? Positive. And by writing it in this form, it allows me to use this identity. this begs the question, what's going on with negative angles for cosine and for sine? Remember what happens when we're measuring negative angles? When I'm talking about positive angles, I'm talking about this orientation where I'm going up. When I'm talking about negative angles, I'm swinging down the other way. So I have clockwise versus counterclockwise. If I swing down this way, which quadrant am I in? Quadrant 4. Is cosine positive or negative in quadrant 4? It's going to be positive. So what that tells us then, cosine of minus a is the exact same thing as saying cosine of a. Well, once again, if I swing down into the 4th quadrant, is sine positive or negative? Sine corresponds to y. So if you're below the x-axis, what's the polarity on y? It's negative. So what that tells us then is sine of minus a is going to be minus sine of a. These identities are identities that you're going to need to know. These are going to be your polarity, your negative identities. And I can also do the same thing with tangent. I can say tangent of negative a. Well, tangent, I know that's going to be nothing more than sine over cosine. But what was sine of negative a? What was that? What's cosine of negative a? It's that. Take the ratio, you get minus, and what's sine over cosine? Tangent. So we call these functions that have this particular property even or odd functions. An odd function is kind of odd, is whenever you plug in a negative argument, it's like you can factor it out. An even function is when you plug in, and it's as if you never did plug in the negative. These functions are known as even. So what does that say about sine and cosine? Sine's an odd function. Cosine is an even function. And functions which are even are symmetrical about the y-axis. Go back and look at the graph for cosine. The graph looked like this. If you take this half, spun it around the y-axis, you get the exact same thing on this side. So even graphs, even functions are symmetric about the y. Odd are symmetric through the origin. If you look at this graph for sine, it'll look like that. But if I reflect it through the origin, you get that part. Okay. So using these properties, do you see what we can do up here now? You can take this and update. Cosine of negative b is just going to be cosine of b. Sine of negative b, that's going to be negative. Push the negative out front, make the positive negative, and here's your identity. What are some good uses for these identities? Well, let's say for the moment that we want to calculate the cosine of 15 degrees. What? Cosine of 15 degrees? Was that something that we had to memorize on the unit circle? We had to know 30, 45, 60, 120. We didn't have to know 15 degrees. That's not fair. How can I know this? Well, I can make 15 degrees by putting a 30 or 45 or 60 and putting those things in the right configurations. Here's how it works. I got to ask myself, how can I make 15 degrees? And I realize I can make 15 degrees if I take a 45 and I take off 30, that will get me 15 degrees. So I don't have to know what happens here at 15 degrees. I can always reproduce it if I need to. Use the identity, the difference, take it and start dropping it in. Now, what I want you to do is look at these identities for the moment, see if you can find a pattern. They're both cosine, cosine. They both have sine, sine. But what's the discrepancy? When it's minus, that's plus. When it's plus, that's minus. Flip the sign in between. Okay, so what that would say then is we're going to have cosine 45 degrees, cosine 30 degrees. It's a difference, so flip the sign, make it an addition, and there it is. And what was the cosine of 45 degrees? Good old root 2 over 2. What was cosine at 30 degrees? And if you forgot, sketch it out real quick. Are you closer, longer in the x direction or in the y direction? In the x. So that means we're going to get a root 3 over 2. What's the sine of 45 degrees? Root 2 over 2. What's sine of 30 degrees? And again, if you forgot, go back to the diagram. Yeah, the smart one's going to be a half. Clean it up. When you're multiplying radicals, what can you do with the radicands? Multiply them together. We're talking about real value functions. And would you look at that? The denominators are exactly the same. That's cosine of 15 degrees. So I can use this angle sum identity for cosine to help me figure this out if I need to. Okay, let me stop, see if you have a question on it. Suppose you want to look at cosine of 5 pi over 12. How am I ever going to figure this thing out? Well, what I want to do is find some way somehow to build up the angle. The first question is, what really is 5 pi over 12? Okay, so let's kind of play around a little bit. When I look at 5 pi over 12, well, what I want to do is take this back, if I can, to a pi over 3, a pi over 4, pi over 6. Because if I can take it back to these, I know exactly what's going to happen at cosine and sine at these three values. I haven't a clue what's happening here quite yet. Okay, so here I have a 12, and that's a 3. Maybe if I take this fraction, multiply numerator and denominator by 4, I would get that. This one, I could multiply numerator and denominator by 3. I would get that. And for this one, I can say 2 pi over 12, and I can get that. What can make 5 pi? Put those two things together. Okay, so what you do, in other words, is look at the numerator, start taking this thing and ripping this thing apart. You could say 5 pi is going to be 4 pi plus 1 pi. That is completely doable. But here's kind of the snag. 4 pi plus pi does equal 5 pi, and when you use properties of fractions, you could say this. 4 pi over 12, we know that's going to be pi over 3. But you haven't a clue what happens here. You can also take this, and you can make 5 by taking a 3 pi and a 2 pi. So you take your number, break it apart in a way that's going to lead you to some tractable results. Take your fraction, break this thing apart. 3 goes into 12 4 times. 6 times. Now, I'm just kind of curious, if you were to express this in terms of degrees, what would you do? You could use the identity I gave you at the beginning of the term. You can say 5 pi over 12 multiply this by 180 over pi. Yeah, that'll work, but you're going through a bunch of calculations, aren't you? You're looking at it and saying, well, I can't get it that quick. But by doing this decomposition, what's this one? That's 45. What's that one? That's 30. See how fast that was? This is going to be 75 degrees. We got the good decomposition. We know how this is going to break down. Cosine of pi over 4 plus pi over 6. Cosine pi over 4. Cosine pi over 6. Flip the sign. And have sine pi over 4 and pi over 6. What was cosine pi over 4 again? Root 2 over 2. What about cosine pi over 6? And would you look at that? We get the exact same denominator. There's got to be something going on here. I wonder what that is. Why do I keep getting the exact same denominator? That's what the scientists would think. Okay, so even if I'm looking in terms of degrees or if I'm working in terms of radians, I can take the number, I can break it apart and start putting things together. When you're working in terms of radians, it can be a little bit more challenging based upon what's coming with the problem. My recommendation is, if you're having struggles with that, do what we did just a moment ago. Look at pi over 3, look at pi over 4, look at pi over 6, and see what you got to do to make all the denominators match up. You could, once again, say this is going to be 4 pi over 12, 3 pi over 12, 2 pi over 12, and figure out what you're going to need for the configuration. Well, there is an identity for the addition for the angles for tangent, but you don't really need to know that because you know the secrets behind what tangent is. If you know the identity, that's great. It just goes a little bit faster. But it's not something that you need to really memorize. As long as you know what happens with sine and cosine, you can always reconstruct it if you need to. Tangent is nothing more than sine over cosine. So what is sine pi over 12? And what's cosine pi over 12? Well, cosine pi over 12, we kind of did it earlier. It's right here. It's a little hard to see because it's in terms of degrees, but if you take a 45, you minus a 30, you take a 45 minus a 30, what do you get? Pi over 12. So cosine pi over 12, that's going to correspond to a root 6, a root 2 over 4. Now, the question now becomes, what about the numerator? How, oh how, could I ever figure this out? And there are a few different ways of how I can go about this. One thing that we could do is, we know the Pythagorean theorem. We know if we take a sine squared theta, add to a cosine squared theta, irregardless what the theta is, if it's pi, 2 pi, it doesn't matter. As long as it's the exact same angle, I know that that's going to correspond to 1 each and every single time. So, if I want to figure what happens here, things in, and then I can solve for the sine. The question is, whenever I solve for sine, am I going to take the principal root or the negative root? Because whenever you take the square root, you have to stipulate not just root, but plus or minus the root. Okay, a little bit of a snack. But where is this angle located? Pi over 12. It's 15 degrees. Is that in quadrant 1 or quadrant 2? It's quadrant 1. So whenever you take the root, we're not going to really worry about it because we know it's going to be positive. If I'm in the quadrant 2 or quadrant 3 or something, I might need to worry what happens here with the negative root. So I can take that, plug it in. I know cosine. I can take this, drop it in, square that. And it's going to take some time to grind this out, but we're going to get there eventually. This piece would be what's on top. Okay, so yeah, we can definitely take this now. We can start simplifying. And we can keep going along with this, but this is starting to get a little bit complicated, isn't it? It's starting to spiral out of control. I could do this. I can use Pythagorean theorem here. It will work. But the question is, could I find another identity that's going to help me solve this a whole lot faster? And the answer is, you better believe it. Otherwise, I wouldn't be talking about it. So the question is, how to make it easier? Find another identity, like the angle sum identity, like we have for cosine, but do it for sine. All right, so the question is, what is sine of A minus B? And how could we figure this out? Well, what do you know about sine as it relates to cosine? You guys remember some identities? How about those cofactor identities? I can take the sine of theta and I can recalibrate it as 90 degrees minus theta. Or if you want it in terms of radians, that's pi over 2 minus theta. Well, I can take this and I can recalibrate this as nothing more than cosine, let's say 90 degrees. Subtract it off, the angle. That's the angle, A minus B. So use the cofunction identity, link this up, move some things around, distribute, reassociate. Okay. Don't we know something about the addition of cosine with the angles? You better believe it. It's right there. So now apply this identity, cosine of 90 degrees, the first one, and then cosine, the second angle, which is B. Subtract it off, sine of the first angle times sine of the last angle. But guys, what's this? Is that not also a cofunction identity? Smack dab right before us. This is going to be nothing more than sine of A. And this right here, the sine, that's also another cofunction identity. That's cosine of A. And there it is. So making a switch up real quick using the cofunction identities, it led us to another amazing property. Look at the pattern here. sine of A, cosine of B. What happens back here? It switches, doesn't it? Sine of A, switch to trig function. Cosine of A. Cosine of B, switch to trig function. Sine of B. Now, unlike up here where it's minus and plus, what happens when it's minus? It stays minus. It would be a sin to make it positive. Don't you see the sign? So don't sin because you want to keep that sign. Whatever you got to do to remember it, just remember it. If it's minus, it stays minus. If it's cosine, just be cos. Okay, I'm really trying here. Okay, minus plus. Do you think you might be able to figure this one out? How would you get this from that? What's cosine of negative b? What's sine of negative b? It's an odd function, so take the negative and pull it out. Negative times negative is a positive. Don't say negative b, say b now. And there's your angle sum identity for sine. So if I want to figure out sine of pi over 12, yes, I could use the Pythagorean theorem. Guys, that's a little bit over the top, isn't it? Yeah, it's really spiraling out of control. What I could do is use these angle sum identities for sine, and note that I can take pi over 12, and I can express this as a 45 minus a 30. Because again, 45 is going to correspond to pi over 4. 30 is going to correspond to pi over 6. Get a common denominator. See what happens. So I have 3 pi minus 2 pi over 12. Now, I get it. It's going to take a little time for you to really wrap your minds about this deconstruction as you decompose it, pi over 12 into the individual pieces. Okay, so apply the identity. You'll have sine, pi over 4, cosine, pi over 3. We're talking about the sine identity, so it's going to be negative, since this is the difference. And then switch things up. This was sine, so now it's going to be cosine. This was cosine, now it's going to be sine. So the first angle, second angle. First angle, second angle. Pay attention to the orientation. Sine of pi over 4, root 2 over 2. This right here is a half. Root 2 over 2. Root 3 over 2. Take this, simplify it, throw it up top. A root 2 minus a root 6 over 4. Simplify it. Keep change flip. And there it is. So much easier using this identity than the other identity. What you're going to be held accountable to is what these identities equal. The derivation, not so much, but you need to know this, you got to know this, this, and this. And you will have a quiz probably next week, looking at all these different identities that we're going to be looking at for the next few days. You already know a few of them. You know your cofactor identities, you know your reciprocal identities, you know now your sine identities. Sine's going to be an odd function, cosine's going to be an even function, tangent is also an odd function. Now we know these identities right here. My recommendation is take some note cards out, make sure you're familiar with it, memorize them, look at a few a day, so when it comes time for the quiz and also for the exam, you're ready to go. Okay. All right, you guys have a great day. I'll see you Wednesday.
I hope that today's lesson was a positive and an encouraging learning experience. and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.